inclusion, sustainability.
That's what Research Matters is about.
What matters now is creating new materials that can impact everyday life.
What matters now is connectivity.
The economy and the environment.
Technology.
What matters now is public education.
Global impact, understanding our place in the universe.
Freshwater resources.
Food security.
Better data.
Brain potential. Health.
Energy.
Digital literacy. Safer food and water.
Culture, environment, and health.
I believe that what matters now is to learn how to live sustainably.
That's my cue. All right, ladies and gentlemen, good evening. Good evening and welcome to McMaster's Innovation Park. My name is Moel Bestawi. I'm McMaster Vice President for Research and International Affairs. And on behalf of Dr. David Chance, my colleague from Algoma University, and my colleagues from all of Ontario's universities, we are so pleased, we're very pleased to have you with us this evening. Tonight, we are talking about what matters now. It's a great question, a question that university researchers think about it all the time. Some may think that university research is a bit removed from the immediate concern of everyday's life. But for those of us who work in the sector, we know that nothing could be further from the truth. That's why we started Research Matters, a campaign to show the public just how much our research really does matter and how it's making a difference. It's an expanded version, if you will, of McMaster's Science in the City series, for those of you who are familiar with this series here in Hamilton. The researchers you'll hear from tonight and those who will engage others across the province this year will speak to issues like safe food and water, strong communities, sustainable living, and economic competitiveness. It is no exaggeration. It's no exaggeration to say, if you are concerned about an issue, any issue, someone in an Ontario university is studying it. Research Matters is designed to give you access to the individuals at the forefront of these studies, to help you find out more about how university research, how your dollars, your tax dollars, is improving the way we all live, work, and play. Ladies and gentlemen, it is now my sincere pleasure to introduce our moderator for this evening, Pia Chattopadhyay, to guide our conversation. No doubt Pia is familiar to many of you. She frequently hosts CBC radio programs like The Current, The World at 6, and Toronto's Metro Morning, and often fills in for Steve Paikin on TVO's The Agenda. She is, in fact, the perfect fit for our discussion, as she's used to asking the tough questions, getting to the bottom of so what and why should I care type of questions. And equally important for an event like this one, she'll keep us on time and track. Ladies and gentlemen, please join me in welcoming Pia.
Thank you, and welcome to everyone. I have failed, clearly, because we're behind time, so we've got time to make up. I want to welcome you all here, and thank you to McMaster for having us all here tonight. You are going to hear from 5 researchers from very diverse universities across our province. They are going to be taking on the question about what matters now. Their presentations will be short, about 7 minutes. I'm going to give them the hook soon after that, so we're going to keep them short. And they are really going to be conversation starters. And we will continue our conversation by asking questions of our researchers. You will all have a chance to do that, as well as we'll be taking questions via Twitter using the hashtag #WhatMattersNow, because many people are watching this on a live webcast. As Dr. El-Bestawi talked about a little bit, Research Matters is really an initiative by Ontario's universities that began last year. The topic last year was Life in 2030. And while it was an appropriate topic to be talking about, and still is, we spend a lot of time as human beings talking about the future, what our dreams are, what our plans are, what the next big invention is going to be. And I feel we spend very little time talking about what matters right now. So I'm really glad that that is the conversation that we are having tonight. Before you came in, or when you came in, you all got a device like this, I think, right? So what we're going to use those for is we're going to have a little bit of audience engagement. And we want to ask you what you think, because as Dr. El-Bastawi said, that university researchers are really engaged in the here and now, and we all have a stake in that. These are our universities. We pay for them. We're engaged with them. The research that comes out of them is important to each one of us. So we want to know what you think matters now in terms of university research. To that end, we are asking you to choose, and I will explain that in just a second, one of these 5 topics about what matters now. Get them up. So number 1, how can a community be a force for social innovation? 2, how safe is your water? 3, is small the new big for material science? 4, is there life on other worlds? And 5, how do our brains work? So you can pull out your clicker now, and you can just lock in your answer by choosing 1, 2, 3, 4, 5 as they correspond on the screen here. If you press the wrong button, you can press it again, a different button, and it will lock in your last answer. So if you guys can all take just a minute to do that, we'll poll the audience now. Anyone not have a clicker, by the way? Anyone need a clicker? Can you put up your hand high so we can get you a clicker? Thank you. There's one gentleman up here as well. 2 gentlemen. 3. Okay, maybe we can keep the polling going and I can keep talking over that. Is that okay, SJ? They're just going to get a few more clickers. We'd ask you to hold on to your clickers because we're going to ask you again to use them a little later on in the evening. We aren't going to bring up our answers now. Once all the answers are locked in, we'll bring them up a little bit later in the evening. A few more hands up for the clickers. Here comes Michelle. There you go. Right there on the right there. Great. Okay, so everyone, if you could lock in your answers 1 through 5, pick 1. Okay. Well, our first speaker tonight is from Toronto, and so clearly what matters now is Mayor Rob Ford. Even if you're from Hamilton or Toronto, you've probably heard enough about that, so he won't be speaking on that. In fact, he'll be taking us to worlds away from Rob Ford. His name is Ray Jayawardena. I told you I was going to screw it up. Ray Jayawardena, who is a planet hunter at the University of Toronto. Ray J, as he is known, is the author of the 2012 book, Strange New Worlds, The Search for Alien Planets and Life Beyond Our Solar System. He has an upcoming book coming out just in time for Christmas. It hits shelves in December. It is called Neutrino Hunters, The Thrilling Chase for a Ghostly Particle to Unlock the Secrets of the Universe. Christmas gifts. Very good idea. Good. You know, you'll be the hit of the party at Christmas if you give a book like that, right? They'll say, what is this about? You say, you have to read it. I saw this guy in Hamilton speaking. Ray says what matters now is the question, is there life on other worlds? Please help me welcome Ray Jayawardena.
Thanks, Pia. I'm just going to wait a second to hopefully get the slides up here. Good evening, everybody. So my question for tonight is one that's been an age-old question. There we go. It's easy to forget now that just 20 years ago, we knew of only one planetary system. And that planetary system had 9 planets. Remember that? Wasn't so long ago. And then, in the intervening years, we astronomers managed to lose, or at least demote one, which made quite a few people very unhappy. School children wrote us letters calling us heartless or worse. Cartoonists had a field day. And there was at least one protest march that I know of in New Mexico. And 4 state houses in the US passed unanimous resolutions declaring that Pluto shall remain a planet. What do these astronomers know? But in the midst of all this commotion, we've actually gained many, many new planets. In fact, after centuries of speculation, decades of false starts, now we know of scores of other planetary systems circling other suns. And this is truly a revolution in our understanding of planets beyond the shores of our own planetary system, and understanding how they came to be, what they're made of, how they compare to our own. In fact, thanks to searchers with telescopes on the ground and in space, as of today, we have 1,000 confirmed planets circling other suns. 1,000 confirmed planets. That just happened this month. Plus another 2,500 planet candidates discovered by, in particular, this Kepler spacecraft, which was staring at a little patch of the sky for 4 years continuously before it had some technical difficulties a couple of months ago. With all of these thousands, literally thousands of worlds that we're discovering beyond the shores of our solar system, we're beginning to get a sense of how we stack up. In particular, among these thousands of candidate planets that Kepler has discovered, a handful are starting to look a little bit like the Earth in that they're about the same size as our planet. A few dozen of them appear to be at the right distance from their stars, such that they're not too hot and not too cold. They could sustain liquid water on their surface. In other words, we have a few dozen planet candidates now that, in principle, could harbor life as we know it right here on Earth. At least in a few of these cases, in a few of the cases of extrasolar planets, as we call them, planets that circle other suns, we can learn something about what they're made of, their atmospheres, and even their climate by, for example, tracing the changing phases of the planet as it goes around its star. Just like we see the phases of the moon, we can measure the light changing as different parts of the planet get illuminated as it travels around its own star. And in some cases, we can also take crude spectra of the planet. This looks like one big mess. Using a whole series of telescopes on Earth and in space, we're able to make measurements of what the atmosphere of these planets are made of. And that tells us, hopefully someday, whether those planets harbor the right kind of chemistry to support life. The kind of spectrum that we hope to take in the near future is something like this. What we're looking at here is a spectrum, actually, of our own planet, the Earth, as reflected on the dark bit of the moon. When you look at the moon, you see a crescent moon, and the rest of the moon isn't completely dark because Earth light, reflected sunlight from the Earth, is falling on the moon. We call this Earth shine. So by taking a spectrum of this bit of the moon, we can actually see our own planet in reflection. And when you look at the spectrum, what you see are all these molecules like water, oxygen, carbon dioxide, methane, ozone, these molecules that we tend to call biosignatures or indicators of life. So the hope is that someday we could point our telescopes at a planet circling another star and measure the presence of these kinds of molecules. And if several of these biosignatures are present at the same time on the same planet, that might tell us there is life on it. The problem, of course, is that even if you had all these biosignatures detected, you still wouldn't know whether you're looking at a planet full of slime or civilization. That's a big challenge. Unless, of course, we happen to detect artificial radio signals coming from the same planet, then we would know not only is there life, there might be life with technology. That might make a huge difference. Even if we can't decode the message that is in the radio signal, just the fact that there's somebody at the other end, a messenger sending it out, will tell us a lot. It would be interesting to think how we would react, how people would react to the realization, to the first compelling evidence, not just speculation, but true compelling evidence that we are not alone in the universe. It's indeed a big question, and we don't really know till it happens, but it might not be that far in the future. It's worth considering. So I just want to wrap up by saying that we truly are witnessing an unfolding revolution in our understanding of our own place in the universe. It's not an exaggeration to say that this moment in history is not that different from when Galileo turned his telescope at the heavens for the first time 400 years ago. In particular, when he pointed at Jupiter and saw 4 little dots, the 4 biggest moons of Jupiter, and he could track them night after night and show that these 4 moons circled Jupiter, they orbited Jupiter. There was compelling evidence for the first time that not everything in the universe revolved around the Earth. That was a dramatic realization. And the kind of discoveries that are coming through the pipeline right now are completing that understanding, are helping us truly understand how we measure up, how we stack up, how our solar system compares to others, and also whether we are alone in the vastness of the universe. Thank you.
Thank you, Ray. Well, so Ray gravitates towards alien worlds. Our next speaker is more attracted to magnets. Very different, diverse. Murali Murugesu is an University of Ottawa researcher. He studies tiny, high-density magnets. These magnets can be used to build faster, more cost-effective computers. So that's good for all of us because we all use computers. And he's really, in his work, keeping the information revolution moving forward. What matters to him is the question of whether small is the new big for material science, though in talking to him before, small is everything about him right now because he has a 2-month-old baby at home, and so he loves talking about small things. We talked about his child before. I won't ask you to do that now, but congratulations on having your first son. If we could invite Murali Murugesu to the stage, he will be answering the question, whether small is the new big for materials science.
Thank you, Pia. Good evening. I would like to start this talk by mentioning a nice talk. And if you remarked in the slide, one of them was the Pluto problem that people were putting up billboards saying that size doesn't matter. But actually, in my world, it does. So here I'm going to talk about small matters that matters for us. Okay. So is small is the next new big thing for material science. If I ask you in the audience, is there anyone who doesn't have a smartphone? Please raise your hand. All right. And the same people, I'm going to ask you the same question. Do you own a computer? Or is there anyone who doesn't own a computer? See? That means we are all guilty. We are whether using smartphone or computers, we are using the similar technologies nowadays. So what I'm going to talk about, the effect of the modern society and the amount of energy we are using in an everyday life, when it comes to computers or smartphones, it's hard to quantify. Really, we don't know how much energy we are using. We talk about fossil fuels and we talk about CO2 pollution, but we never think about how much energy we are consuming in everyday life that we in this ever-growing modern technology world. So if you, just to give you an example, this is the new or future $1.2 billion Canadian communication security establishment in Canada. And they are building this brand new building, and it's going to host one of the most powerful, if not the most powerful computer ever built in Canada. And this computer is going to consume electricity equal to what is enough to light the whole Ottawa region. So you can imagine the amount of power a computer can consume in one single day. So what matters now for us is to create new materials that can basically revolutionize what we are already using and consume a lot less power and perform way better. So in this quest, just a memory lane, if you remember, some of you might have used these tape recorders. You know, I'm from the generation, I saw the evolution of this, from cheesy tape recorders to, you know, floppy disk that virtually disappeared. And then from there, we have the hard disk technology. In the old days, the hard disks were like 2 gigabytes or 10 gigabytes, and nowadays we are talking about terabytes. And then these came along in the early 90s. From there, we can get smaller and smaller memory storage devices. This is a small key. We can already store a lot of information in simple memory key. And now we are getting into these solid state devices. Basically, these are hard disks as well, but in a slightly different technology. The question I'm asking is, what is next? So if we are going to create devices that are going to be better performing, basically the future matters now. We are creating material that's going to impact in the future. So in this quest, basically what my research group is interested in, creating materials that can store information. That means store memory storage devices, hard disk technology. We can simply think the storing as a simple binary unit. That's all computers are working at. We can use this as an interrupter or the switch, light switch, whether you can store information in a state 1 or 0. So these are information storage. But in reality, a computer stores its information in a memory such a way that all the spins are aligned in a certain way. This will be equal 1, and the other information is aligned in a different direction. So this is what we are storing. So in order to store that, if you look at a computer hard disk, you have these magnetic domains. These are quite large, and these contain hundreds of metal ions. In these metal ions, you can only store one information. That means each these domain can whether store 1 or 0. So in order to create high density storage, you need to make these domains smaller. So you can make material smaller and smaller dimension that you can make these tiny domains. But actually, there is a law which predicts that as soon as you get certain limits, they will reform much larger domain, and therefore you will lose your information. So in order to overcome this problem, we have to really tackle this problem in a different way. This is called the top-down approach. That means you're cutting down into smaller pieces. What we are envisioning is bottom-up approach. That means we are building molecules. These molecules are atomic scale. That means atom level. Each one of them can represent hundreds of these molecules can be stored in the same size area. So we can store a lot more information in a small region. So we call them nanomagnets because they are in nanoscale dimension. As I said initially, size matters in this case. So imagine you have an atomic scale technology. You can see today's technology is shown here. We can envision storing this much of information in one single device. For example, this is a cartoon version of it, but actually in reality we can perform or create devices 100,000 times better performing and consuming a lot less energy. So the goal is to create faster, cheaper. Everybody wants to get cheaper electronics, that's for sure, and also energy efficient so that we don't consume or we don't continue to consume as much as energy what we are doing now. Therefore, we believe the research matters. This is the research group in my group, and this is the University of Ottawa. My lab is situated, and we are funded through this funding agency, and therefore, we strongly believe the research matters, and today's technology will revolutionize tomorrow's day life. Thank you.
You know, if you presented this a few weeks ago, you'd get no CSEC jokes, but you might get a few now. Thank you, Murali. When we think about university research, I think most of us think of science and technology, but we have to remind ourselves that research going on at universities is much broader than that. And our next researcher comes from a different perspective. She comes from Ontario's newest university, Algoma, which is in Sault Ste. Marie, in case you didn't know that. And Gail Broad studies concepts like social economy and social entrepreneurs. And it's interesting, I was talking with Gail before, and she spent 25 years before going back to school to study this area as a community organizer. And we were talking about what would the community organizer be called today? And it would be called a social entrepreneur. But it was interesting all those years that she was doing that work, that term wasn't even invented. So it's a real new branch of research. We do tend to think of entrepreneurialism as something that only belongs to the business world, but many social issues, things like homelessness or activism, are affected by the principles and concepts that parallel the world of traditional economics. And so Gail studies the ways that these social principles can enrich or impoverish a community. So for Gail Broad, what matters now is how communities can be a force for social innovation. Please help me welcome Gail to the stage.
Thanks very much. Yeah. Is that okay? Can people hear? Yeah. Yeah, today's social and economic issues are really complex, in my view, and the solutions require a lot of creativity on the part of the people in the communities surrounding them and that are coming to deal with them. In fact, people that are working to resolve some of these really complex issues need a number of characteristics, and many of these characteristics are very similar to the kinds of characteristics that we associate with the people that are highly successful in business. So they need to be risk takers, they need to have very diverse perspectives and be able to think right outside the box. They need to be people that are very flexible, that they can change and move and be very agile. Of particular interest to me right now in the work that I'm doing is that they need to be people who can combine business skills, who can take the skills of business that we need, of looking at the bottom line closely, of figuring out how to allocate human resources and so on, and combine those of a successful entrepreneur with the social conscience of a community activist. And those people need to be team players. They need to work in communities, and they need to be able to find ways of working in very diverse communities. And a lot more. They need a lot more than that. In the short time that we have together right now, I'm going to give you just one example of the complexity that I'm talking about, the multidisciplinary issues that are facing the world, that are very concrete problems that we're trying to solve, and the innovative solutions that a community of people can design to address those issues. And I want to conclude my remarks with why communities are, I view, a force for social innovation. I work mostly in communities across Northern Ontario, and if you've ever had the chance to fly or drive across Northern Ontario, you know that in the region there's at least two things that you'll remember. One is that it takes a very long time to drive across Northern Ontario. It can be 2 or 3 days depending on the speed at which you drive and how many animals you hit along the way. And the other thing that is very striking is the amount of water that we have. The water in Northern Ontario has, obviously a tremendous resource to us, but it also produces a lot of hydroelectric power that the rest of us and the rest of the world really needs to power all of our computers and our smartphones and all of those things. But the vast distances means that there's thousands of kilometers of power line corridors going through forests in Northern Ontario. These corridors have to be kept clear of trees that will interfere with the power lines. And we're talking, as I say, thousands of kilometers. So the problem that we're dealing with, or one of the problems that we see in the north, is keeping those power corridors clear of the trees. And that's often meant destruction of habitat for both flora and fauna, causing problems for species at risk. And it's done through the spraying of toxic chemicals, which is not good for any of us, certainly not good for our environment, and the use of heavy equipment going on and basically logging the areas underneath them. So we lose certain species of trees, but we also lose certain species of animals and birds and a variety of different species. So how do we go about solving this problem? Well, we have a group of botanists that were led by a woman named Sue Meads, and she connected with a group of business people from a few power companies in the north, and together they decided that they would identify low-growing plants that are indigenous to Northern Ontario and plant them in the corridor. Now that sounds like a pretty simple solution. Well, you just need to travel over a few thousand kilometers, identify all the different plants and the different types of terrain that you need to plant them in, the soil and the habitat of the corridor, and start planting the right type of bushes and short trees so that they don't grow tall enough to interfere. A big job, but maybe you don't think that's too complex. I mean, that can be solved. But then there's another whole layer that comes on top of that. And the trouble with a lot of these species is that they only grow in Northern Ontario. And they're not commonly cultivated in nurseries because there's no demand, there's no market for wild plants that are indigenous to Northern Ontario. I suspect that not too many of you have milkweeds growing in your gardens. They're not a plant that you might necessarily want to grow in your gardens. but they're really essential for the habitat of monarch butterflies, for example. So again, we're talking thousands of kilometers across an area that has tremendous differences in the terrain itself, as well as in the climate across the north. So the next question becomes, how can we get the seeds and grow the plants so that this corridor remediation can actually take place and we can actually reduce the level of toxicity in our environment and improve the communities and the way that we live. So this is where social entrepreneurship really kicks in. The first team, composed of the botanists and the business folks from the power companies, began searching for people who would actually know how to do this, how to collect seeds, store them, and so on. And some of that knowledge is knowledge that is inherent within First Nation communities. It's called traditional ecological knowledge. But that knowledge also had to be matched up with the knowledge that the botanists had in order to make the whole thing, feasible. And it also needed to be matched up with the business of actually making this an endeavor that would be worthwhile for the people. So the team found two different nurseries, one which was located at a small First Nation community and the other one located in a Francophone community. In the Francophone community, it was a cooperative that was developed in the early 1980s by a group of women who found that it was really hard to get jobs in communities that were primarily based in logging. So the need to address the environmental impact of power line corridors and remediating the habitat for species at risk, reducing and eliminating herbicide use, has led to the creation of a market for low-growing plants that are indigenous to Northern Ontario. As I say, this has required scientists to work with First Nations, to work with Francophone communities, and the non-scientists involved in this whole project have to learn the skills in seed collection and storage and seedling growth. It's required the communities involved to learn lots of different business skills because even though there's thousands of kilometers to plant, that's still not going to be enough to really support nurseries doing this kind of work. So now they're looking to highway developments and mine remediation sites as a market that they can expand into. So the goal of both the First Nation and La Maison Verte, which is the women's cooperative, is to create jobs and alleviate some of the disadvantages that First Nation peoples and women often find in the job market. So how does all this combination of things link into communities being socially innovative and the development of social entrepreneurs? What our research is showing is that communities can be a molding force in supporting or in not supporting socially innovative solutions to some of the most pernicious social problems. Communities can play a very important role, particularly in supporting the development of young social entrepreneurs. And they're the next generation of people who will be the catalyst for change. As Pia mentioned, I spent 25 years trying to do this work, but it's time for me to pass this on to some others. So thanks to some funding from the Trillium Foundation, last week in Sault Ste. Marie, we brought together about 40 people from across Northern Ontario, many of them young people, most of them young people, but we also brought some more experienced people who are all engaged in changing the face of Northern Ontario. And I think in changing the face of the world. One was a young First Nations woman who's introduced environmentally safe cleaning products to not only her own community, but to nearby towns, and created work, again, not only for herself, but for several other young people in the process. Another was a young man who's helped numerous youth deal with addictions through the creation of a youth drop-in center, and he's funded that by developing a recording studio and a coffee shop. Another has been working with youth all over the world in developing self-confidence and self-esteem through a social enterprise. These young people are dealing with the after effects of things like residential schools and 300 years of colonization of First Nations people. They're finding ways to work across cultures and linguistic barriers to break down the silos that prevent communities from sharing their knowledge with one another. They're finding ways to solve environmental problems, social problems, and building a whole new kind of an economy that is inclusive of the people that are often left behind, all at the same time. So how can communities support these young people in doing these exciting things and being and becoming real social innovators and social entrepreneurs? The young people have told us that there's a number of concrete actions communities can take. We can help them create peer networks, provide spaces for them to meet other young social entrepreneurs, learn from each other. In other words, we can create a real learning community for them where they can share and develop those skills together. They've told us that we can help them find mentors, people that are experienced and are successfully doing this work. They told us that we can provide them with concrete skills and training, with investment advice, and much more. So that's what we're going to be doing for the next 3 years, is researching that. I see Pia's coming up. If we can make that happen all the time, if we can make it happen really frequently, not just sometimes, then we're going to start addressing some of those really big issues like poverty, social exclusion, and cleaning up the mess we've been making on our planet. We think this is research that matters, and it matters now.
Thanks, Gail. Hello, hello. How's everyone doing? Everyone good? Everyone liking what they're hearing so far? Okay, we have 2 more speakers to hear from. They're pretty smart, eh? Yeah. Well, if you thought we couldn't get any brainier, brace yourselves. We're about to get brainier because our next speaker used his own brain, the own power and smarts of his own brain, to produce another brain. That takes smarts. Chris Eli Smith studies theoretical neuroscience at the University of Waterloo. Chris is interesting for a lot of reasons. One of them is that his discipline is quote-unquote non-traditional. He studied engineering in his undergrad. He went on to do a master's in philosophy. His PhD is in philosophy, neuroscience, and psychology. So he's sort of done what we all talk about universities should do, is do cross-disciplinary things and bring them together, and that's what Chris has done. Chris's creation, it's an artificial brain called SPAWN, S-P-A-U-N. He will tell you why it's called that. And SPAWN is teaching the world about everything from mental illness to new computing methods. And Chris is arguing that what matters now is figuring how our brains work. Chris.
Thanks. Imagine if we understood how our brains worked. We could help millions of Canadians who suffer from mental disorders and save the country upward of $51 billion a year. We could test new kinds of drugs and new direct brain stimulation techniques to help us with everything from Alzheimer's to stroke, while endangering far fewer humans and other animals. We could build new kinds of machine intelligence to help us with everything from the complex to the mundane. Imagine having a robot that could do your chores for you, or a web assistant that could help you research some complex problem. And most of all, it would just be really cool. It might even change how we think about who we are. But how are we going to do this? How are we going to understand what is one of the most complex physical systems in the universe? The brain has 80 billion neurons, almost a quadrillion connections. It's more powerful than the most powerful supercomputer, even that one we saw before, but it only uses the energy of a compact fluorescent light bulb. It weighs about 3 pounds, but it controls everything that we do, think, and feel. So how are we going to understand the brain? In fact, Richard Feynman, the physicist, had a suggestion that we can use. After he had died, on his blackboard, the following was written. It said, "What I cannot create, I do not understand." And in fact, many researchers in my field have been adopting this suggestion and essentially thinking that if we really understand how the brain works, we should be able to build one. Now, by building a brain, I really mean building a computer simulation of one. Just like you might build a simulation of an engine of a car to show that you know how that works. In the case of a brain, we want to simulate individual neurons. So we'd want to simulate the input coming into those neurons in the form of ionic currents. And we want to simulate the output in the form of brief pulses of voltage. And if we simulate hundreds or thousands or even millions of these neurons, and maybe most importantly, if we understand how to connect them together in the right ways, we know that we can get them to perform interesting functions. And this really brings me to the work that's been going on in my lab recently. In short, what Pia said was true. About a year ago, we built what is still the world's largest functional brain model, and it's called SPAWN, which stands for Semantic Pointer Architecture Unified Network. I'm not going to explain that. I just wanted to let you know that it is not in any way evil. It's just an acronym. And Spawn has about 2.5 million of these simulated neurons. And here we can see it performing a simple recognition task. So what we've done here is we've shown Spawn images, just like the ones that would appear to your eye, and they're handwritten digits that we're showing it. It's then using that information to try to figure out what the digit is, so it's doing classification, and then it's moving its arm in order to draw out what digit it thinks was there. And when we run this model, we can generate these kinds of images, which are sort of reminiscent of something like fMRI data that you've probably seen in newspapers. But more interestingly, we can actually read Spawn's mind. We can look at the things that it's seeing. We can watch as it remembers the information that it's been presented with. And we can see as it figures out which points it wants to move its arm through in order to produce its result. And the only reason we can do this is because we've built a computer simulation. So as you can see in the background here, we have all of these outputs I was talking about, these brief pulses of voltage that are coming out of the neurons, and we have access to that information from every single neuron in this artificial brain. And the only reason we have that kind of detailed access to the mechanisms is because we've built a simulation. So I think it's interesting to know that we can take all these sort of brain-like parts, we can put them together, and they can do some kind of interesting function. But what would be far more interesting is if we could show that it could do lots of different functions. One thing that really distinguishes humans from machines is really our cognitive flexibility. So machines are often highly specialized. They're very good at one task, often a repetitive task. But humans, in contrast, are very flexible. We can go from driving a car to answering an email to doing research on a complex problem, all in a matter of minutes. And because biological flexibility is so important to cognition, we thought it was important for Spawn to be able to do lots of different kinds of things. So Spawn can do this sort of recognition task, but it can also count. It can reproduce different styles of drawings. It can do some kinds of gambling tasks. It can remember lists of numbers and so on. And I'm going to show you another task that Spawn can do. In fact, I'm going to let you do the task. So this is a puzzle, and your job is to figure out what goes in this bottom right-hand corner where the question mark is. And this kind of puzzle is actually one that in the animal kingdom only humans can solve. So it's a difficult puzzle. And I've given you a brief moment to look at it, so hopefully you'll have some idea what goes in that last square. And if not, we can watch Spawn solve this puzzle. So we can see as the information is presented to Spawn through its visual system, and it's really trying to figure out what the pattern in the digits is here. It's never seen this set of digits before. So it's using its visual system, its memory, and other parts of the brain in order to figure out what the pattern is in those digits. And then, when it comes to the end, it's going to write out its answer. And because it's a video, it gets it right every time. Now, it was important for us to show that Spawn could do these kinds of tasks because we wanted to argue that our methods are not only useful for things like doing recognition tasks, which in fact lots of animals can do, but they can actually do tasks which are cognitive, essentially uniquely human. And we not only wanted to show that it could do those tasks, we wanted to argue that it's doing these tasks in a human-like way. So here's another task that Spawn's doing. And this is remembering a list of digits. And we can watch those digits as they're loaded into the working memory. But you'll notice that one of the digits begins to fade. It's essentially forgetting that information. And so as it's writing out its answer, when it comes to that number 8, it actually draws a horizontal line to indicate that it doesn't know what's in that location, but then it completes the list. And if we give exactly this same kind of task to humans, they make these same kinds of errors. In short, just like you, Spawn remembers the beginning of the list and the end of the list much better than the middle of the list. And this is true for any length of list. So what we've done is we've simulated millions of neurons, and we've got them to do interesting things. Now, I'm the first to admit that Spawn is much simpler than a real brain. It only really knows about the digits from 0 to 9. It only has about 20 of the 1,000 or so brain areas that we know about, and it only really has parts of those brain areas. It, in fact, has 40,000 times fewer neurons than we find in the real brain. And, of course, it does way fewer tasks. But it is a huge improvement over what there was before, and I think this is why research like this matters. In short, Spawn uniquely combines biological realism with actual function, with actual behavior. So now we can begin to use the model in lots of different ways. So we've built models like Spawn that help us understand cognitive performance and the effects of aging on cognitive performance. So for instance, we take a model like Spawn, we show it a lot of actual intelligence tests, we can collect its results, and then we can see what manipulations can we make to make those results decline. And in this way, we can come to understand why we get dumber as we get older. Right? This is no way to sugarcoat that. We can also take models like this and damage them. So we've built models like SPAWN, damaged them, and looked at the effects of stroke and shown that different kinds of interventions can help alleviate those effects. We can look at the effects of drugs on brain function. So SPAWN has a dopamine signal in it, and dopamine is one of the major targets of drugs for Parkinson's disease. And we can also use the knowledge that we gain from SPAWN to really answer some interesting questions like, what is the difference between biological computation and digital computation? And this is why we've been working with groups around the world to actually build the next generation of powerful, efficient computing platforms that work more like the brain. We can also look at these models and extract algorithms from them. We've extracted algorithms from models like SPAWN to build new kinds of controllers for robot arms, for quadcopters, and to understand natural language. In short, I think SPAWN matters because it's beginning to give us a sense of how the brain actually works. Thank you.
So if you're a fan of Chris's, I want to tell you that on November 15th, he's going to be hosting a program, 6 parts, on Discovery Channel. It's called Stephen Hawking's Brave World. November 15th, 8 o'clock, Discovery Channel. The only problem with that, that's when the agenda's on. So you have to pick between Chris and maybe me, more likely Steve Paikin, but you can watch Paikin or I at 11 and watch Chris at 8. So that's on November 15th. Our final speaker tonight is the hometown guy. John Brennan is from McMaster. John's trying to find simpler ways to know if water is safe to drink or not. I don't think I need to explain any further about why that matters, given what we've seen happen in this province and around this country in the years past. John's research involves a bioactive paper. What is that? That is, it reacts to pathogens or poisons, making it cheaper and easier way to discover contamination. And naturally, what John will be arguing is what matters now is how safe our water is and how to test how safe our water is. Please help me welcome John Brennan.
Right. Well, thanks to everyone for making the trip to Hamilton, whether it was from near or far. So what I want to be able to sort of get across today is a little bit of the research we do, but also to try to give you a sense that while we're trying to make what might be conceived of as a very low-tech device, a simple paper test, in order to actually get that, there's a lot of very high-tech research that has to go into the front end of that. So I'm one of these poor guys who doesn't have a clicker, so I have to keep yelling next slide all the time. So next slide. All right, so this just gives you an indication of just a few of the problems that have occurred over the last decade in terms of water quality. So probably one of the most, I guess, memorable ones was the Walkerton tragedy. So this was an E. coli 0157 outbreak in the year 2000. A whole bunch of people died, several thousand people got sick, but there's a lot more to it than that. There's all kinds of problems, boil water advisories, there's issues in terms of the quality of beach water. How many times do you hear that there's beach closures because of E. coli? So this is a problem that has been around for a long time, and it's not one that's going away anytime soon. So next slide. If we want to ask how do we currently test our water, whether it's our drinking water or our beach water, the top shows a very basic test. It's a basically a microbiological test to look at E. coli. So we have these little petri dishes and you see these little dots. So on the left you see a few dots. That water's not too bad, but it still wouldn't be drinkable. On the right you see something that's fairly contaminated. And this is how we currently do testing for E. coli. On the bottom, you see this great big device called a liquid chromatograph mass spectrometer. That's currently how we test for things like pesticides. So if we ask, why are these not good enough? Well, this takes 48 hours, lots of time. This, you probably don't have one of these sitting in your kitchen. I do, but most people don't. These cost a lot of money. So this setup's probably about $750,000. So what we want to do is get around the time and the money. And we took our inspiration, next slide, from this. So you can go into the drugstore today, or the pharmacy, and you can buy one of these. This is a home glucose test kit, or test meter, or you can buy one of these. So, pregnancy kit, right? What these both do is they use a biological element, something called a protein, that is interfaced onto a surface. So what we need to have happen is you have to be able to take biology out of its normal environment, which is us, and put it into this very artificial environment onto some surface and keep it alive. So in this case, there's an enzyme called glucose oxidase, which when it binds to glucose, which is what we want to detect, gives an electrical current, and the current's proportional to the amount of glucose. This one uses something called an antibody. Antibodies are part of our immune system. This particular antibody binds to the pregnancy hormone, and within a couple of weeks of getting pregnant, what will happen is, not pregnant, 1 line, you get pregnant, 2 lines. Antibody flows along the surface, gets captured by a second antibody, and a little gold label gives you a color, little line. So how many other things can you go into the drugstore today and buy that will allow you to do these kinds of tests? Not many. So the reason is, as I said, it's very hard to keep biology active when you put it on an artificial surface. So how do we get around that? Next slide. And way down here, there should be an arrow. There it is, and if we hit that, what you'll see is a robot. So this is how we do it. We make thousands and thousands of slightly different bio-inks that we ultimately can print. So we have a whole series of robots that do tasks for us, and at the end, we find things that we can print using piezoelectric printing technology. So all of this gear is very, very expensive and complicated to use, but at the end of the day, what we do is by screening tens of thousands of different potential inks, we find the one that is printable, that will give a color change or an electrical signal, that will keep a protein active, that won't allow fouling, and all these things. So because we're asking multiple questions at the same time, by screening, we can get multiple answers. So once we've done this, next slide, the goal is to go from the millions of dollars to the $30. Actually, this one's probably closer to $100. It's really fancy. It's got, multiple cartridges. So what we've been doing is taking these inks that we can then put into standard cartridges, into standard inkjet printers, and print our tests. So we're looking at doing this in 2 ways. One way for the North American market is to go with a big printer and print lots and lots and lots of strips. One of the problems with that when you're talking about moving this into the developing world, so places like Kenya or India or France, is that what you ultimately get, is a stability issue. If we're going to try and put this in a warehouse in India where it's going to get to 50 Celsius for some length of time, biology will die. So one of the concepts we have is, why not print it on site? If we can make something where you now have the software, you have the ink, and you simply have a piece of filter paper you put through, you print your own tests. And voila, you can test your water. Next slide. So here's 3 examples of tests that we've developed in our lab. So this one detects organophosphates. So what's an organophosphate? Long ago, these were the pesticides that we used to spray all over our lawn. In the developing world, these are still used. They've been banned in North America for 3 or 4 decades, but these are widely used in the developing world. So what will happen is we import food from India, China. It's been sprayed with this. We can use this to test. Another thing that you will find is chemical warfare agents. So in Syria, there was a big issue with chemical warfare agents. These strips will detect those compounds directly. So we have the ability to detect these kinds of things with a simple test where we get a color change. This one detects heavy metals. This particular test is designed to detect mercury. And you can see that we get a nice color change. Both of these tests use an enzyme This is a biological element that converts a molecule to something that, in our case, is colored. And in this case, the pesticide inhibits the enzyme. It's an enzyme called acetylcholinesterase. It's in your body. And what happens is if this gets inhibited, you go into neural shock. So this is how it actually kills you as a chemical warfare agent. Mercury, obviously bad. We have a different enzyme, gets inhibited by mercury. This one detects E. coli. And the key thing with all three of these tests is that they're able to detect these species, in these two cases, well below the regulatory limit. In this case, we can detect at the limit needed for beach water. We're working towards the limit needed for drinking water. Next slide. So we also have developed this fancy thing called the iPhone. I wish. But what we have done is we've developed an app for the iPhone. So this app allows us to take photographs anywhere that we want of our strips and ultimately quantify the color and convert that to concentration. So now you use something you already have to get your signal. And next slide, it geotags it. So now you go out in the field, you take a photograph of the strip you use in the field, and you then have, at McMaster, we have a website called WaterMap that this iPhone sends all the data back to. So we can now map the water, look at whether it's safe to swim, say, way up here in northern Quebec. I don't know. Apparently not. It's red. That would be bad. Of course, around Hamilton, everything's red. I don't know why that is. But the idea here is that we can go and figure out the quality of water, map that, and do this in real time very, very cheaply. So last slide. Thank you for your attention. And this is why I think research matters.
Thank you, John Brennan. Thanks, John. I'm going to ask our 5 researchers to come up. We're going to get chairs set up and get them all mic'd, so it's going to take us a couple minutes. I think we're going to get that done. So as soon as the chairs are up, you guys can come sit down. I want to remind people who are watching us on the webcast that you can tweet us. You can tweet us if you're in this room too and you're too shy to ask a question at the mic. The Twitter handle is What Matters Now, hashtag What Matters Now. We are going to take questions from our audience. Michelle, who is somewhere, I will see her. There she is. She's going to be running around with this microphone. So if you have a question, you could just raise your hand, and Michelle will be coming up. As well, when you came in earlier this evening, we had a bowl. We asked you to put your business card in it. Sorry if you didn't have a business card. But we decided we would draw one and give you this fancy schmancy Research Matters hockey jersey. And Dom here has drawn the name, and I can't read her writing, so I have to call this again. Is it S-A-U?
S-A-U-T-U,
Sautu? Jetu? Is that the... McMaster? From McMaster? Are you here? Oh, of course she did. This is her jersey. Her jersey. Do you want to grab it for her? Okay, perfect. Are we up? Okay. So we have, I think, about half an hour or so for questions from the audience. We'd like to involve as many of you here in the audience to ask questions. We will be taking some from Twitter as well. I just ask you to direct your question, whatever researcher you would like. We're squished up here. And the researchers will be debating these questions amongst themselves as well. So does anyone have a question? Anyone want to raise their hand? We'll get the microphone to you. Okay, I'm going to hand this off.
Yes, I have a question for John Brennan because I'm very concerned, I'm sure like a lot of people are, about safe water, especially safe drinking water. I don't go to the beach too much, but a lot of people do. I've been reading in the paper recently about microscopic particles of plastic that they're finding in water now. And my concern is about the detection of that and what are the health hazards for it, because these are sort of bioagents like germs and then heavy metals and things like that. But this is something else. Is plastic that inert that it can't be detected anyway this way? And if it's not, how can we know what are safe levels? We can't get rid of it, but what are safe levels?
So in terms of the plastics, depending on the particle size, there's really 2 issues. If it's big enough on the micron scale, it's actually easy to detect using simple microscope imaging. If it's really small, there's actually a whole field of research on nanotoxicity. And what happens is when these get down to the nano scale, they have the potential to go into your cells. And then we don't know what happens, right? That's an ongoing question. One of the things, though, to be worried about is you may think the plastic itself is problematic, but there are no surfaces that are inert. So on the surface of the plastic, you may well have metals, pesticides, other things adsorbed, and those are really going to be the things you need to worry about. So detecting that in terms of imaging that the plastic is there is one thing, but ultimately being able to determine what's on the surface is going to be the key. And that's one of the things that we're working with some of these test strips.
Oh, good. Thank you.
Anyone else have a question? Over here, Michelle.
John, I think you're very popular tonight. Another water question. That's the reason why I made this long trip here tonight. We are very much involved with water, safe water in rural areas in different parts of the world, very isolated. How soon before we have, in your view, the likes of an iPhone that will be able to connect from anywhere in the world?
So the iPhone technology itself, the smartphone technology, is actually ubiquitous. So we've had researchers in Kenya. We have researchers currently in Kerala province in India, and they're actually really set up in terms of the cell phone technology. Now, they tend to use cell phone rather than the smartphones that we have, but almost all of these still have cameras. So the potential even to use a camera on one of these phones and then email the result somewhere centrally to be analyzed exists. So these are things that we've actually talked to people in the field about, and we've been doing field trials in these sorts of places now, and these are exactly the kinds of questions that come up. Not everybody has an iPhone or an Android phone, but you can get around that as long as you have a camera phone of some sort. We can do this.
Thank you.
I have a question for John also, I'm afraid. Sorry, John. I work for a company that manufactures ultraviolet disinfection treatment systems, particularly for rural well water. So I'd be very interested in the ability to have a very quick detection for E. coli. So I'm just wondering, how soon might we get to the point where something like a test strip kit could be included with the ultraviolet disinfection equipment?
So this is a really interesting question, because it actually comes to the point of how do you get technology out of the university and into the real world.
Right.
And there's a thing that we call sort of the innovation gap between these two. So what we've been doing over the last probably 3 years since we've developed the E. coli test is working with a company in Kingston, a company in France that are big water testing companies, and having them do field trials, do validation studies, and generate the data that we have to have before we can go to Health Canada, go to the EPA and to the other regulatory agencies and actually get approvals to use these. Right. So at this point, it's less of a technical hurdle in terms of scaling up the strips, which is another project we have ongoing, and much more of sort of a regulatory issue that we need to go through before we can actually commercialize these. Okay. So this is why when people ask, you've developed the strip, why can't I buy it in the drugstore tomorrow? It's all these extra steps that have to be put in place before you're allowed to do that.
Right. Okay, perhaps we can take that offline sometime, because it'd be a big interest for our company.
Thanks.
Thank you.
Hi, I have a question for Dr. Ray J. My question, I guess I just want to pick your brain a little bit on how you feel that humanity, as a whole would react should we find some sort of conclusive evidence of intelligent life on another planet. Do you think it would be, from the spectrum of mildly interested to, borderline scared?
Sorry, that's an excellent question, but of course a big one, right? In some sense, I've thought about this and discussed this with a number of people. When my book came out a couple of years ago, Robert Sawyer, who's a science fiction writer, well known to many of you, I'm sure, Seth Shostak, who's a scientist at the SETI Institute, doing these radio signal searches, and myself were the panel. And when this kind of question came up, Robert Sawyer said, well, if you look at the Gallup poll, 60% of Americans think the alien's already here. So if you go out and say, oh, we found a radio signal from alien, they're going to say, hey, big deal, right? I mean, we've known that. So it's actually kind of hard to predict. I wrote this op-ed in the New York Times that I just kind of flashed by in one of the slides. And my own take on it was that if it is these kinds of biosignatures, kind of traces on a spectrum of a distant star with a planet, it may not be a long-lasting news story. It may last a week or two, and then most people in the world will go on with their lives. And while scientists spend the next decade kind of nailing that down and really making it a secure detection. However, if it is, I think, an artificial radio signal or some other artificial signal that signifies technology, I do think that would be hard to ignore. It's one thing to speculate about aliens. It's another, to see, movies from Hollywood. But it's another thing to really kind of say, okay, now, we have to recognize that this is real. I think that might be a much more dramatic and much more harder to ignore kind of detection. One other thing I quickly want to say is that I also think that even if it doesn't have a huge impact overnight, because most of us manage to accommodate a lot of new information without really changing our minds, over generations, I think it will. In the same way that Galileo and Darwin's discoveries have changed our perspective of ourselves, I think over generations at least it'll be quite a big deal.
Got a question from Twitter for Chris. At what point do we have to consider the rights of artificial brains?
Not yet. Yeah, this is an excellent question, and one which you might think as a philosopher I'd be interested in answering, but I would prefer to leave it to other philosophers. Essentially, I think that we're going to have to address this issue the same way we address this issue when it comes to animals. So, there are lots of debates about how similar is animal consciousness to human consciousness, which presumably will play some role in our deciding whether we have to give them certain kinds of rights or not. Clearly, we give lesser rights to animals than we do to humans. Maybe that kind of thing will happen with the brains that we decide to build, but maybe that will also depend on the kinds of behaviors that they exhibit. So my suspicion is that while a lot of people try to sell this as a new kind of question, we'll use the theoretical constructs we have now for dealing with other kinds of rights which aren't necessarily human rights in trying to deal with that issue as well.
A question for Chris. Have you considered the question of qualia? That is to say, whether spawn might produce percepts and feelings?
Right. So for those of you who don't know, so the question was, have we considered whether spawn exhibits qualia? And qualia is a philosophical term which is supposed to identify the quality of an experience. So the standard example would be when you see a red rose, what is it like for you as a subjective individual to experience the redness of that rose? And I, like some other philosophers of mind, don't think this is actually a well-formed question. So I think we are not in a position to basically ask that question of spawn, again, any more than we could, or even a more complicated model, any more than we can get at it very well with humans and other animals. So when we attempt to ask these questions of other animals, for instance, so we can ask a monkey, or we can try to determine, does a monkey have what it's like experience when it sees a particular kind of stimulus in the world, we essentially have to ask that question by getting it to exhibit a particular behavior. Now, without getting into too much detail, the reason the notion of qualia was sort of posited in the first place was to get at the idea that behavior was not sufficient for understanding subjective experience. But I think, again, in the case of even other people, but especially other animals. It's clear we can only decide how conscious or how much of a subjective experience another individual or another animal has by looking at its behavior. And I really think that the same thing is going to be the case with these artificial brains that we're building as well.
Anyone else in the audience have a question back there? There's a couple.
Sure. Question which I will direct to Gail, but actually throw it open to everyone, which is when you were talking, it's an interesting thing, the relationship between being a researcher who is subject to peer review scrutiny and that sort of thing, and also being involved with your community and community building. And I'm wondering if you see that as a conflict or a benefit. And then for everybody, I'd like to know, this evening aside, but how much of when you're doing your research, are you just thinking, oh, this is kind of a fun question I'd like to know the answer to, and how much are you thinking about the impact of that research elsewhere?
Well, there's lots that's been written and talked about in academic circles around, you know, the values of being an insider research versus being an outsider, and, you know, the concept of objectivity and subjectivity. And I think I mean, speaking from my own experience, what I find is that you have to be really aware of not only how you perceive the community that you're working with, but also what their perception of you is. And so I always try to determine whether, is this a community that I can work with where what I'm doing is going to be really can influence the outcome, or whether I will be, whether the way that this community perceives me is going to really color how they respond or how they're going to be working with one another. But I also think that it's absolutely valid and crucial. Like if you're going to be working with a community through a process of change, then supporting that community in it and understanding where the strengths are and helping them build on their strengths, which is something that an insider researcher can do very well, is really crucially important. So usually there's a team. We do a team approach to doing the research. And there was a second part to your question about.
I think the second part was really for everybody, which was just a sense of how you balance the strictly seeking new knowledge, not knowing what you're expecting in some sort of neutral way, versus am I doing some sort of societal good? Am I doing something that's good for the world? If that enters into the equation at all.
Yeah, and I guess to answer that question, I mean, I find that that because we do, in the work that I do, it's community-based research. So that means that the community comes to us with the questions, with the problems that they're trying to grapple with. And so very often what happens is that it's not necessarily, it isn't my curiosity in the beginning. The community brings that to me, and I always become engaged with them and find it, incredibly compelling to explore that with them. And often it's the relationships within that community that make that exploration so rewarding, both challenging and rewarding. We work with a lot of small communities where people in the community know each other. They're often related to one another. In First Nation communities in particular, there's often strong connections, one person to another, and so that brings with it a whole host of challenges, but the rewards are very great when you see a community taking leadership and developing in the direction that they want, and choosing a direction for themselves and going there. So.
Anyone else want to pick up on the question from the audience?
Sure. I'm going to take a slightly sort of different angle on it. And I think that these two questions about, are you doing it because of just interest, intellectual curiosity, or for a particular purpose, they are more deeply linked than people often think. And I'm actually kind of concerned that there have been some movements in government and in funding agencies to overemphasize the immediate impact. I mean, sorry that this is about research mattering now, but Sometimes the immediate impact is essentially overemphasized, and recently it's become much more difficult to get funding for the questions which you can really only justify because of your intellectual curiosity. So, my personal story is something like, I really wanted to understand how the brain worked. I thought this was fascinating. I had some background as an engineer, so I took a mathematical approach. And what we essentially did by accident is discover how to program an entirely different kind of computing platform than what you typically find in standard digital computers. My suspicion is that's going to have enormous impacts. Not yet, but we sort of have good reasons to think it will down the road. But if we were forced, 10 years ago when we started the research, to say, what is the impact of your research in the next 3 years, which is now how much of funding is tied to, we would have not been able to express that, and we would have not had any funding to discover something I think is kind of relevant. The one other example I'll use is, Mike Lazaridis, CEO of Research, or ex-CEO of Research in Motion, put tens or hundreds of millions of dollars into research that he knows is not going to benefit his company, regardless of how the company is doing or not. He knew this 5 years ago, investing very heavily in things like quantum information processing and fundamental theoretical physics. And to me, that has a kind of foresight which we're lacking from a lot of the kind of funding that's currently available.
And I think that's, just to follow up on that, it's one of the real challenges in community change. Doesn't come about overnight, and most of it, there's no roadmap to follow. So you're always exploring, like, is this going to work? You have to try that out. You have to be really flexible and finding those things that are going to fit within the history and the culture and the context of this particular community that you're working with, and most of that kind of change is a very long-term process. And the idea of this outcomes based, that at the end of this 1 year or whatever, that you're going to be able to identify all of these, outcomes and say, oh yes, the community is completely changed. I mean, that's not the way it works. And I think, as Ray was saying, that you're looking at generational change, right? Like, you're looking at perceptions and attitudes and knowledge bases changing over a long period of time. I think it's one of the greatest challenges in doing any kind of really valuable research. Thanks.
Hi, this is for Gail. I wonder about these terms, social innovation and social entrepreneurship, and do you have any concerns that your work could be diminished in a way because you're kind of marginalized because of that? Certainly the engineers and the health scientists and the business folks don't. They talk about innovation, they talk about discovery, they talk about entrepreneurship, and I just wonder what you think about that.
Yeah, I do a whole political analysis on terms like social capital and social entrepreneurship, and share those with my students from time to time. But absolutely, one of the great challenges that I've found in this whole blending of the economic and the social is that as soon as people hear social, it is immediately downgraded and doesn't command the same respect or interest. I mean, if you take a look at what governments are looking at in terms of funding and funding support, what you find is that anything that has the word social attached to it, is really downgraded. It's very challenging, and so I think in some respects that's the reason that some people have latched on to words like social entrepreneurship and social innovation. And I have lots of hesitation sometimes in using those terms. And I do try to encourage people to really analyze why are we trying to turn, or why do we feel that we need to link business terminology with what, community development or community activist. I mean, that was the term that was being used 20 years ago, but today it's social entrepreneur or social innovator. How do we tell the difference? I mean, I personally don't see a difference in the actual work that we're doing, except for the fact that I find that some people believe that you don't really have to have different principles underlying the work that you're doing, and I think you do. I think that you have to be very clear about what your principles are when you're going into this work.
Sorry about that. Thank you so much for the jersey, and thanks for some really great talks. It's really, I'm learning a lot. My question is for Ray J. I was wondering, you said that if we could detect radio signals, we'd be able to tell more about lives on other planets. So could you say what's the status of that research, and maybe what are some of the challenges with detecting it, and when do you foresee perhaps maybe we'll detect some of those signals? Thank you.
So what I meant was the kind of the search for artificial signals intentionally sent out by, or maybe unintentionally sent out by another technological civilization. The term that's used is SETI, the search for extraterrestrial intelligence. It's been at some level going on for 60 years now, but at a very low level, right? I mean, it's also the challenge is, we live in a galaxy with a couple of 100 billion stars, right? And here we are in sort of 2/3 of the way out from the center of that galaxy, first looking and surveying our own immediate neighborhood, and then trying to expand the search a bit further out. Now, the other interesting thing is that since we've had television transmissions, I believe starting in the 30s, radio transmissions and television transmissions, those have been leaking out into space from the Earth, and that sphere of broadcast basically is expanding out. So if there were highly advanced technological civilizations in the very immediate neighborhood, sort of 10, 20 light years away from us, in principle, somebody could have picked up our signals, our unintentional signals from 70 years ago. So in some sense, it's sort of one of the questions is, is it possible that even though we have these huge numbers of planetary systems in our galaxy, and the signs, all the evidence to date point to there being likely lots and lots of habitable planets, could it be that maybe, and also we do see lots of ingredients for life, complex molecules in interstellar space, in dust disks surrounding newborn stars. So the stuff of life, the ingredients of life might be common, the habitats might be common, and yet could it be that maybe life even originates but doesn't always or often last long enough and evolve into complex technological beings? So I think either way we're going to learn a lot in the next decade, partly because our ability to detect other signals is growing in leaps and bounds. The challenge, of course, is it's the kind of search that the opposite of sort of, impact today kind of research, where you don't know when the answer will come. So it's a bit of a challenge in terms of funding. A lot of the funding for SETI has dried out, and there's only a few sort of privately funded efforts, particularly at the SETI Institute in California, that sort of carrying out the search for other radio signals. It's the challenge of also kind of the needle in haystack case, where you don't know what frequency somebody is going to be broadcasting at, from which direction in the sky. So it is a bit of a blue sky search, and it is challenging to keep that going. And yet, just the search and also what we find out, at least about our immediate neighborhood, will tell us a lot about who we are and how special or not we might be. And that might be, worth finding out as Earthlings, all of us together.
I have a quick question while the microphone's moving. So you showed a picture with 5 planets, and the Earth was the little one in the bottom right. Were those artists' conceptions?
Absolutely.
Okay, just checking. I just want to make sure.
The artist conceptions, but their sizes, the relative size compared to the Earth, are measured sizes. So my point was trying to get at the sense that we are now finding planets. Just today, 10 new planets in the habitable zone between 1 to 2 times the size of the Earth were announced. So the other thing I wanted to emphasize was that the pace, not only are we finding lots of planets, but the pace of discovery is in fact accelerating. And it's very sort of an exciting time to be part of it. And one story I love to tell is that my first year PhD student from the University of Guelph, who came to Toronto to do a PhD with me. I mean, she doubled the number of planets with those phases measured. There were 3 measured before, and she found 5 more. So she more than doubled by herself as a first-year PhD student the number of planets for which, Kepler planets for which we actually have measured those variations in light. So it's exciting because one person at a young age can just get into the field and make an interesting finding, right? It's sort of a little bit like the Wild West, where there's a lot going on and there's room for exciting discoveries literally every week.
We've got another question on Twitter, and this one's from Early. When and how might your research be commercialized?
Very good question. In every research, such as this one, there is main problems. They always comes with. There are positive points and the negative point. That's why we do research. So in this specific area of research, these magnets, they behave at magnets at below certain temperature. We need to be able to bring these magnets to function as magnets at room temperature, so that we can have computers, in everyday lives that containing these magnets. At the moment, they behave as magnet at low temperature. So if we go to Mars, maybe we'll be able to use them as, hard disk memory storage devices, but, at the moment, unfortunately,
it's not a collaboration.
Yeah, there you go. There you go. So that would be one way to perceive. So it could be we are making great progress. It could be in the next 5 years. It could be in the next 10 years. But this is research. You cannot specifically say tomorrow is the day we're going to find it.
Hi, this is a question for Marley again, actually. Today at work we had a hard drive crash and we lost some data. So I thought of 2 things when I saw your talk. First is that if we put all those hard drives in one, it's a lot more data we lose at once potentially. But also questions these days with security and people who don't want data to be found or people who want to recover data. How does your technology address that? So does it improve the fragility nature of the data, or?
If you take the current technology, the newest computers, they are having these solid-state drives. 5 years ago, these solid-state drives didn't really exist other than some fancy computers. Solid-state drives are basically like flash memory that in your camera or small key that you use. They never made the bigger disks simply because they are not very stable. So they crash. So if it's a small memory chip or memory key in your camera, if it fails, you don't care. It's cost $20, so you just change it to another one. But if it's a hard disk, then there is a massive damage. For most of us, the data is more valuable than the computer. So in your case, for example, I understand your pain. But how our molecules can do that, basically, the way you are putting these molecules, how they are separated, you can control at molecular level and engineer them. And that's the greater power you have, the bottom-up approach, compared to the top-down approach. That means we are cutting these particles smaller and smaller. Whereas we are building molecules, we are engineering them at atomic scale so that we can design and stabilize them. So hopefully, this is the way to go for. And somewhat, if you may, I wanted to answer your question as well. Earlier on, you asked about how, today's research and tomorrow's technology. If we didn't do these research 50, 60 years ago, we wouldn't have computers here today. So that's something we need to think about. And we do need those computers to do these brain calculations,
And to find.
Yeah, exactly.
Is that all the questions we have from the floor? Okay. We're just about out of time, but I did want to ask him, Ray, I'm going to put you on the hot seat a little bit, which is, and I don't want to open the Pandora's box of funding for research, except for to ask you this. Compared to your other 4 researchers on the stage and like many others, your scientific research costs a lot. You need big equipment to do it, that big science money, funding, and approaches. And I just want to put you on a hot seat a little bit about asking you about, in this day and age where funding, we've talked about this, has been cut back, it's hard for you guys to get funding in some instances. Is it a time when big science needs to be supported, or should we be supporting smaller initiatives when it comes to research?
There's sort of, it's a spectrum and not only in one direction, right? It's not only just big and small, but it's also kind of the most applied versus the most blue sky kinds of research. So there's, I think quite a mosaic of research that need to be supported. In terms of my own work, I mean, it's not motivated by trying to make a better computer or trying to make a better toaster or anything like that for tomorrow. And yet, the fundamental research that we do often end up providing practical benefits. I mean, the most extreme example and the well-known example is, when Faraday first played with a magnet and a coil, and he could see that moving the coil and the magnet relative to each other would produce a current. And the Chancellor of the Exchequer in Britain came to see his lab and said, well, of what use is it? And Faraday's answer, which was quite brilliant, was to say, sir, someday you will be able to tax it. Right? I mean, and forget research that led to computers. We wouldn't be here without electricity, right? So you don't know where it will lead at the time that you're, quote unquote, playing with it. So in that sense, I think we really do need to kind of support a broad range of research across, not only in terms of size scale, but also in terms of the immediacy or the focus or lack thereof. And I also think, I mean, to go back to the earlier question from the floor as well, I mean, I think that we need to think broadly about what the benefits are. The benefits aren't simply a better computer or a better toaster. It's also the inspiration for the kids who might go build those things, and they might get inspired in astronomy class and go do chemistry. I mean, it's not sort of so easily predictable all of the fallout that comes out of research, because all of us here are not only researchers but also educators. I mean, we take our passion and our knowledge to the classroom and to the broader world as well. And I also think that science is an integral part of human culture, and it makes us all richer. I mean, it's not all about just having a faster, better phone and better bread. It's also about sort of feeding our minds and brains. And I think research gives us a lot to chew on in that sense as well. So.
Actually, this decision has been made in my field. So I don't know if people have heard recently, but last February, the United States, on the heels of a €1 billion project announced in the EU, announced their own $1 to $3 billion project. Both of these focused on neuroscience. And that is a very big and surprising change, right? So in fact, in this time where you might think that research has been scaled back, sometimes what's happened is the money has been handed out in huge chunks, basically so the researchers can worry about how to deal with the issues of giving the money out. And this has upset a lot of people, unless you are on those teams. You can imagine that we'll see what happens.
Can you apply this now?
All 5 of you for this really stimulating night, and thank you all for coming out to Hamilton, except for you. Thank you for coming here from your nearby resident. And I hope you guys all found it stimulating. I want to call upon you to give these guys a round of applause. Thank you. And I think we're going to come unhook your microphones now. And as they do that and don't get tangled up in one another, you remember at the start of the evening, we asked you to pull out your clickers and vote on what you thought mattered most now. I'm going to ask you again to pull out your clickers now. And after hearing our 5 presenters, if you wouldn't mind clicking them again, whether it's your same choice or if you changed your mind a little bit about what matters most. And we'll put them up on the screen again here. So number 1 is, how can a community be a force for social innovation? If you think that's what matters most now, click on that. Number 2, how safe is your water? Number 3, is small the new big for material science? Number 4, is there life on other worlds? And number 5 is how do our brains work? So if everyone can just take a minute and click on our answers, and then we'll bring up the two screens to compare them. Okay, we all clicked? Yes, anyone still clicking? We're good? Okay, so let's bring up the slide from earlier when we began the evening, how you guys, what you thought mattered most. Let me see if I can interpret this data. I might need help from one of our researchers. Okay, what is red in your first slide? Okay, so at the beginning of the evening, how safe is your water? Half of you thought that was the most important area of discussion in terms of what matters most now. Look at that, it changed. How do our brains work? That's what came out, 51%. Anyway, it is interesting because just to see the changes, but also to remind us, people often ask me what my job as a broadcaster is, and a lot of people, as a journalist is, and a lot of people say, oh, my journalists say, well, my job is to inform you. I actually think of it a bit differently. I think of being a journalist, my job is to help make people think, and I think that's a job of researchers as well. They gave us a lot of food for thought tonight. It is just the beginning of a conversation, and it sort of all ties back into what this evening is about why research matters. And I'll just go back to what Dr. El-Bastawi said at the beginning, which was that we often think that research is sort of confined to the halls of academia, and perhaps sometimes researchers don't come out in the public as much as they should. But this is a way to get what happens in our universities across this province into conversations around our dinner tables and with your friends. We heard lots of interesting things tonight. It's really important that we share the message, pass the message along about what we're hearing. So, when you're out for dinner this week or going out for coffee, tell your friends about the cool thing you heard about brains or water or computer chips or life on other planets or social innovation, and help us spread the conversation throughout our communities. I think that's it. I think I need to call David Shantz back up to the stage. Up to the stage for the first time. David was introduced at the beginning by Mo. David is the VP of Academic and Research at Algoma University.
We'll have some fascinating conversations this evening. They're gone. I had something riddled out in my head about community innovation and helping me think better through clean water and small computers to find outer space beings that will keep our engineers, both of whom are my sons, in business. So, good group, and we want to thank each one of you for coming and spending this evening with us. We also want to thank all of you, and just to say that we hope you enjoyed tonight's discussion, and to remind you that for this community, for you and for many others, this is a start of a conversation. It's not an end. We can continue this conversation, and more information can be found on the Research Matters website and Facebook and Twitter. Right now, we'll continue our conversation in the atrium, which is out here, and for a short reception, coffee and says refreshments, and there's certainly much to discuss. One housekeeping item, you will find a friendly person or two at the exits here. Please remember to drop off your clickers so we don't have to go find new ones at the door. And thank you all for coming tonight. Please keep in touch.